Thanks, Tom, for the introduction. I completely missed it because I was so fascinated by what Gultman's doing here with my laptop and the whole setup. I'm also very grateful for Nico's presentation this morning, because he showed exactly the type of slides that I would be so proud of making myself. But my slides are very, very lo-fi, as you will see. But nevertheless, I wanted to, so I came up with this title on cloud-based analysis of Earth observation data using open source software. Why did I do that? Where did I come from? Tom said this briefly. I did a PhD in geostatistics, analyzing groundwater quality monitoring networks in the Netherlands. And as a byproduct, there was some software development that I then open sourced in 1997, that was. And it was an interesting affair in those days. That software then, that wasn't programmed in C, because C was the only thing that you could use in these days to sort of, work on several platforms. That was the only thing that was portable. Later on, we got things like R, and I started to use that. We had S+ before that, but that was also, license mess and stuff. And so we moved to R in 2003, and so I started doing that and discovered that I would never do something else, because otherwise you would move from one environment to the other and go to the GIS and go to R and go to your standalone applications and so on. That was in those days. And then suddenly when things would work in R, you said, okay, everything apparently works in R, right? And you're done. Basically, you can do your graphs, you can do your regression, you can do your statistics, your data management and everything. And so that's not something particular with R, but the same thing is true for Python, right? It's very convenient if you're a Python user that you can do everything in Python, right? That is a reason why you would stick to that. So we started doing that, and together with Roger and Virgilio, we wrote this book in 2008, Applied Spatial Data Analysis. With R, that was also the year that I moved to University of Münster from the University of Utrecht, in Amsterdam, where I had been before. So there are papers on what we do. So the key thing in R was that we sort of brought up classes for spatial data, points, lines, polygons, grids, and methods for them, and that could be reused by other packages, and that could then also be used for interfaces to GDAL and to GEOS and stuff, so that other packages didn't have to worry with this bloody GDAL thing. So it's a separation of concerns that sort of caught on, and that sort of triggered a whole lot of other packages that were then developed in R for spatial data analysis. And then in 2016, we redid everything with sort of a modernized way because a lot of things had changed. And we also wrote a new book, which is Spatial Data Science with Applications in R, which appeared 2023, which is completely freely available online. The link is there down there with code and everything. And now we're actually working on a version of that says with applications in R and Python, where all the code chunks are both in R and Python, which is a bit of work. Why this title? So as I came out of spatial statistics and geostatistics and so on, so you can wonder, what does this guy do in Earth observation data? It was mainly triggered actually by frustration, what I saw that we are now collecting all these data, and that I saw there is so much friction in using it, right? That everyone sort of, if you looked what people would be doing, it was sort of tough. Cloud-based will become obvious when we heard the numbers, right? What was 34 petabytes or something like that, the kind of numbers where you think, that's not going to work when I download. First, open source software is sort of the short answer is they're not because it's cheap. Well, it's also cheap, but there's a cost to everything. But basically because for doing proper science, you need to be able to see what's going on, right? So you need to be able to scrutinize the code that you're using. And I always say, if students write a paper, use Microsoft Word, that's fine, because I'm not so interested why these letters come at these places on the paper, but I'm interested in the computations that lead to a certain graph or a certain map or something, like a certain table, right? So what we used to do, it very roughly, I presented this 10 years ago at an EODC meeting is kind of the classic workflow from Earth observation. Download mosaic images, correct them geometrically, regrid them, match and shift time so that things put together things, and then you run some algorithm and you collect results. The typical thing is that we publish this in the paper. What we do, we run the algorithm, we describe the algorithm with equations and so on, and we show the images that come out. But that you need this thing to reproduce the thing, right? So if I want to check that or do that too, I have to do that too. And the whole first 5 steps is a big mess. I mean, in the sense that if you start to download, you have to put images somewhere, and group A will do it this way, group B will do it that way, and there it starts, right? So we ended up in the 10 years ago situation where we had all these sort of groups doing platforms and doing big data and so on in different ways. Some in public clouds like Synergize with the Sentinel Hub, and Google Cloud on the Google Earth Engine with the Google Cloud, and then Vito and so on, and some on private clouds like the Veren. And that would be basically work for the group and grow incrementally. What happens when things grow incrementally, and when students, supporting things go away every 3 years and so on. So, you probably know what happens when you do that. Yeah? It's not very sustainable. And also it's very embarrassing to share, which is logical, right? Because it grows incrementally. So it's a mess. And so you don't want to share that. Here is a Slido. So I talked about open source. Here is this question whether Google Earth Engine, I couldn't set up a Slido. I only have 2 questions. So we're going to do that by raising hands. So is Google Earth Engine an open source thing? Who says yes? Who says? Okay. Is it a little bit open source? Okay. Yeah. So is it not open source? Who says not open source? Okay. So that's interesting. So there's a majority. That I'm very happy I put in the B option, because there's a majority being for B. Yes. So, right. So why is it? Could somebody say why it's a little bit open source? Maybe we can discuss that later on, right? I would argue it's not open source, because any Google Earth Engine function you call ee.something, that's a function call in the Google Earth that actually does something, calls a function. The function that it calls, you cannot read the source code of that, right? There might be a misconception that because you're writing a script and you can share the script that you're writing, that, some people think that makes it open source, that because you're exchanging source code. But the actual things that happen, right, the actual processes that happen, you cannot get to the source code of that. You cannot put it somewhere else. You cannot take it, you cannot get it, you cannot read it, you cannot install it somewhere else. You cannot run Google Earth Engine on another computer. Yes, is that the proof of the pudding? I hope. So, it's pretty much the same thing with ArcGIS and the Python interface. You work with Python and you think, oh, it's open source because it's Python, right? But you're calling all kind of ArcGIS functions of which you cannot see what they do, right? Because you don't have the source code of that. Anyway, what we came up with is an answer 8 years ago, is a project that started that developed openEO, which is an API, which is just a technical layer that does nothing but translate things. Yeah, so it doesn't compute anything, but it says these platforms basically all try to do the same things for you. Yeah, 90% of what they do is exactly the same all the time, right? They just do it in different ways. And if you do something here and you don't understand it, and then you say, okay, let's try to do the same thing with the Sentinel Hub, and you get 2 different results. Who are you going to ask and see, where did this go wrong, right? Who is going to help you? So that's a problem in terms of understanding what's going on. So what we did was at least sort of create something that shares, sort of picks the shared element in terms of the names of the processes and says, well, this is how we're going to name them. And then we're going to make connectors to these existing backends that then actually do the work. And that is now something that exists, that has been developed, is still under development. It's not perfect. And that is actually offered also for free, and nothing is for free in this world, but sort of you can get free credits for this on the Copernicus Dataspace ecosystem. And Pratigya on Thursday or Wednesday or Thursday will hold some workshops on this, some tutorials on how this works. So that simplifies things. The image there, the metaphor there is. Could you, by the way, start a clock, because I don't have a clock myself. Thank you. Nice. Got 10 minutes extra. The metaphor there is, of course, GDAL, which is kind of the Swiss Army knife in all our open source software, in the sense that it reads and writes raster and vector data, and that everything open source uses GDAL to do that. Yes, and you don't see it all the time, but it happens, and it's very convenient because it also creates some common understanding how things work, right? So if you have a new data format, you just have to write a driver to GDAL, and all these softwares on top of this slide will be able to use it, right? Without any modifications, right? I mean, you need to shift a couple of versions. You need to wait some time, but that happens. So we wrote this blog in 2016, which basically initiated this whole openEO idea, and I was probably the strongest proponent of this, because of my frustration that things were so difficult at that time, and they're still difficult, but they're at least easier nowadays, and there's more understanding. So one thing that I would actually like to talk about clouds and data and things, how you do things, is about how you represent data, how you put data on disk, how you represent images and arrays. And then 1 month ago, I ran into this blog post from Jared Kiefer and Juliet Signal, both from Element 84, chunks and chunkability. And then I thought, oh, this was exactly what I wanted to talk about, and they just wrote it down. The thing is that this is a blog post I recommend strongly for you to read. It's pretty technical, right? So it goes into the deep elements of where chunking, where his array formats come from, what the old versions were like 50 years ago and so on, and what the versions are now, which is mostly cloud optimized UTIF and ZAR. And we'll talk a little bit about this, about that one. Yeah, so the problem is basically, how do I store pixels in a file, right? So we think mostly images, right? A file is an image like a GIF or a PNG or whatever, or a JPEG. And the simple, stupid way is to, if you have a 16 by 16 raster, is to sort of just go to line by line, right? That is the common way images are stored. So the first line just has the first set of pixels. That means that the index goes from left to right. So and we think of this as the x coordinate or longitude, right? If we think of spatial images, and then the rows are then the rows go down, and that's basically the y coordinate, and that means that when your indexes increase, you go down, although your y coordinate goes up, right? Your y coordinate typically increases when you go north. Row numbers go down in matrices. Yeah, so this is the way we do things, and this works. Now we are in this unique place, the WIC, and everyone sort of hasn't by now probably experienced how it is to live a few days with an internet that has the speed of the internet that we experienced some like 15, 20 years ago or so. So this is a very joyful thing. We had this in the tutorial of Christoph yesterday, where we had to wait for things, and that was the same thing 20 years ago. This is the same thing now if we want to do things and download images on our regular networks with real imagery. So if you work with Sentinel-2 tiles, yeah, they're large. They take a while to download. If you work with these tiles over a continent, over Western Europe or something like that, or a country like whatever, Germany or Poland, so a serious country with serious service, then that takes a really long time. So it's not like this is an imaginary problem. What we see is when you browse the web, is when you do Mastodon or Blue Sky or so, you see that these images actually are kind of they're filling the screen. First of all, they're empty, and then you wait a while, and the image fills the screen, right? So it means that it's really reading all these pixels. While it reads it, they come in over your slow Wi-Fi. It's filling it, and that is not the most efficient way. And actually, the web 20 years ago, times of early browsers, work with modems, right? We had modem connections 20 years ago in laptops. They would make this noise that fax machines also make. Fax machines are, I won't talk about what fax machines are. Anyway, they solved this problem, right? Because everyone's looking at it, everyone wanted to do shopping, so they solved it. So what they did is actually interlace the imagery. So what they would do is not order your pixels this way. This means that you read it completely and you only see sort of, you have to wait 5 minutes until you see sort of the top 10%. So what they did was, so they interlaced pixels and sort of put them such that you would get, by reading pixels, you would first get a coarse version. Yeah, you get this pixelated image, and that pixelated image was then filled with sort of a finer version and an even finer version. And then in the end, you get the full version, right? And if you think about, looking at a Sentinel-2 image, it's 10,000 by 10,000 pixels, right? Now, who has 10,000 by 10,000 pixels on their screen? So you can't even see this thing, right? So if you view these things, you're actually always looking at a lower resolution version because of the screen resolution. We use this, we don't do this much anymore because networks are now so fast that images that fit on the screen are there before you have scrolled down, right? So I think this is a thing that has gone by, but what we do in Earth observation is work with overviews, with pyramids. So we have a full resolution version of the 10 meter, 10,000 by 10,000 pixels. And then we have these overviews, which are, by factors of 2, are lower resolution versions of the same thing. They're called overviews or an image pyramid. Yeah, Earth Engine does that in its own format, but cloud optimized UTIFs typically also have them. So here's the question 2. My Slido 2 with raised hands. So if I do this, right, if I go from this image and create overviews in Sentinel-2 image, I have these overviews, I'm looking at them. Then the top left pixel, right? So this pixel on the 2x2 overview, what is it? Is that the mode? It represents this section of the original image, right? And the value in this pixel, is that the mode, the majority class of the underlying pixels? Who says yes? The most occurring class? No, good. Is it the median of this area? Yes, there are a few yeses. Is it the mean of the underlying area? There are quite a few hands, I would say 30%. Is it the value of the center pixel? Let's say there is a center pixel somewhere in the middle, a pixel value. There are hands, but somewhat fewer. Or is it the value of the top left? Is it this pixel here that it takes? There are also some. So there's only question A which was not answered. We're divided over the other 4. Yeah, so we're working with overviews all the time, but we don't know what they are. I don't know what they are. I have a suspicion. I think it's if they're created incrementally, it's probably the top left pixel. If they're if you would do it simply, you would take the middle. But it's a single pixel in any case. If you take means, that is of interest, but you get a new variable that has much less variability than the original, right? So you get you get other properties, other statistical properties in your overviews. So I have suspicion. You can control these things. When you create overview, you can actually tell GDAL, with GDAL add O, which is add overviews. You can give options and say you should do it this way, this way. You can even do the mode if you have categorical data. If you do this for soil types or so, you should take the modal category, of course, not just or you at least that could be a good idea to do that. Anyway. So now comes the question: what is cloud optimized, right? We have all these things, and like the product that OpenGeoHub now creates is that. Oops, I pushed. Oh, it works still. The products that OpenGeoHub creates, sort of on a monthly or even weekly basis, are global coverage or something on the 30-meter level resolution. And a lot of these things are, as Leandro showed yesterday, are easy to use. So they're massive files. They're files that are so large that you would never think of downloading the complete file, but you can easily use them in quantum geouse. You just say where it is, and you can zoom and pan and so on, and you work with that. So idea is that essentially with minimal effort, you can efficiently read small and large portions of these massive files, right? That is basically what it does. So the files are big, but you don't need all of them to use them, right? Because you're probably not going to use them completely. So you might use them, for instance, on a lower resolution, right? If you want to view them for a very large area, you don't need all the pixels, right? You need to only look at a low resolution representation. So you should be it should be possible to read low res, which are these overviews. One key here is that you do some clever chunking, that you kind of look where is the data stored. And the thing is that chunking can serve several purposes, and it gets harder if these data are more complicated. So for instance, if you have a time series of satellite imagery and you're interested in time series analysis, if then all the data are stored band by band by band by band, for a single pixel time series, you have to go through all the bands. Yeah, so this is basically the option A that I have here. So this is X, Y, and this is then time. If I store them as bands, so to speak, which is a common thing in cloud optimized geotiffs, you would have to take a pixel from every band. If on the other hand, you know in advance that everyone's going to do time series analysis on these data, you would store them as time series. Yeah, you get the first pixel, put a time series somewhere, then put a second time series, third time series, and so on. And of course, you can do all kind of compromises between these two. There is all kind of possibilities. Yeah. So this is what chunking is, and chunking is something that you can choose and you can optimize. The question is, optimize for what, right? The people looking at spatial averages, for every time slice, you want to compute the area that's flooded, something like that, right? So you would do a global operation on the whole map for time step 1, and then for time step 2, you want to go through the bands. But if you do a time series analysis in the sense of fitting time series models or so, you want to have each time series separately. So there is there is the optimized word, but there is not a clear target. There's not a single identifiable target, I think, I'm afraid. So this is a lot of text. This is the what GDAL info gives you when you give it the Sentinel-2 file. It basically says that you have here 4 sub-data sets, 10 meter, 3 sub-data sets, 10 meter, 20 meter, and 60 meter imagery, and that you have to dig into that to get some real imagery. So this is a sub-data set. That's the very long name you see in the top, where you see the coordinate reference system going here. And then it gets here more interested. Here it says this is the origin, and this is the pixel size, 10 by 10 meters. If you would go down in this information, you would see that for every band, you would see that it has overviews. So here are the overviews. So this is roughly 10,000 by 10,000, right? So this is the first 5,000 by 5,000 to 2,700 and so on. So this is 2 by 2 pixels, 4 by 4, 8 by 8, 16 by 16 pixels. So these overviews are there, and they add hardly any disk space, right? But they make use of this data extremely much more efficient if you want to have overviews of these data. Another thing you see here is that it says block is 128 by 128. We saw that before. So this is the blocking that's used. So if you want to read this data, don't read 127 lines or 129 lines, read 128 lines, and it will be fast, because that is sort of the internal file structure that makes it extremely fast. So it's an indicator for the reader how to efficiently read these things. And if you create these files, you can also modify these things. So this is the number of, these are the tiles that I got somewhere from Sentinel-2 from part of the world. So as you see, it covers mostly land. How much data is this? I came to a different number. I typically do the computations wrong, but sort of you could say, well, how large is the Earth radius, and then what is the area of the Earth, and then how many pixels, 10 meter pixels do I have? When I say 1/3 of the Earth is land surface, I have this number of pixels. And then if I have Sentinel-2 for 10 years and an image comes every 5 days, I would have this many, right? And that would give me something like an exabyte for 10 meters. But you came to much lower number, so it's something must have gone wrong in my computation. It's just to point out that this is sort of you're not going to move these data sets, these large. They are somewhere. So they are somewhere, and where they are, we call that the cloud. And so if you want to do something with this data, there is no real options then to go there too. Then what is the cloud, right? So more lo-fi slides. So basically, the cloud is, the cloud is a collection of if it's storage, it's hard drives, right? So we have hard drives or solid state drives. What I just wanted to point out is that both hard drives and solid state drives are collections of discrete things. Hard drives are a collection of disks, and they have sectors and so on, and they have a certain size. Solid state drives are just chips, and they have boundaries and they have sizes and so on. But you don't see that. Sort of that is all abstracted away. You can work with large files. You can say I have a file of a gigabyte. It's much larger than one disk in my hard drive, for instance. So the disk is then in the software layer. You basically have the disk, and on top of that you have a file system that lets you sort of mimic that you have a continuous space, right? You think of it as a continuous linear thing that you can chunk up in parts, which you call files, right? So you have a file system and you have files there, and then you put all these things in a file server, and the file server may have some RAID, but on top of that you make logical volumes. That means that you sort of create a file space over multiple disks. Yeah, so that can become much larger than a single disk, and then you put all these file servers in server racks. Yeah, so this is what the people then do next, or multiple server racks, and then you create some kind of object storage, which is kind of another level of abstraction where you say all my disk space is just stay there, and I can make files as large as I want to, and I have a certain way of accessing them and moving them around, and certain protocols like S3 is a common protocol. And you put these server racks basically in buildings, and the building is called the data center, right? And we typically call that then the cloud. And the data centers also have a limited size, so they're somewhere, and there are other data centers, and they're connected through a network. And the thing is that this network, we think that networks are fast, but networks turn out to be sort of the most limiting thing and the most expensive thing if you want to move around large data set. Yeah, so even moving a large multi-petabyte data set from one data center to another is a very costly and timely sort of time-intensive operation that you would not rather try to avoid. So if you want to compute in on large data sets, you would make sure that you rent your compute infrastructure in the data center that hosts this data. Yeah, so if you want to work with the Sentinel-2 in COGS, then you could go to the Amazon, but you have to go to the Oregon East or something like that, the data center there, because the data is local, and the network in the data center is very fast and cheap, right? Inside, they have a very fast network. Just between data centers is not a good idea. So downloading is okay for things that fit on your screen, but if there are things that no longer fit on your hard drives and so on, it's just a bad idea. It's messy, and it's not sustainable and not reproducible. And so you do things on clouds. What you then do, and what we saw with Leandro's presentation yesterday, is lazy evaluation. So here's an example. This happens to be an R package, the road stars, where we open a Sentinel-2 tile, which has a very long name. But what we do is we read the image, and then we plot it, and we see that happens in that the image on the right is created in 1.5 seconds. But thanks to downsampling, the image, so it says downsample set to 20. That means that I read every 20th pixel, right? And then I skip 20 lines and I go to the next line and read again every 20th pixel. Yeah, so I read 1 in 400 pixels, because this is what we call lazy evaluation. You could say read star should read the thing, right? It's a function, so it should read it, but it doesn't. It says, well, let's wait until something happens with it, right? Let's remember where it is and something happens. Then plot happens, and plot can tell, well, I have to create a PNG from 1,000 by 1,000 pixels. So I anyway only need 1 million pixels from this image, because there's not more than, that's all I can plot. If I would sort of read more than that, then I'm just overplotting existing pixels. Yeah, so that's why it computes roughly, okay, let's do this at the sort of 20 downsample level, sort of 20 by 20, that means 200 by 200 meter resolution, and read it, and then GDAL picks the overview that fits that and sort of reads from that overview. And that's why this is in 1 second. If you would say downsample is 0 and don't downsample, then it would take like a couple of minutes or so and give exactly the same result. So that those are things that are, that we learn also from Google Earth Engine. If you use it interactively, it just computes pixels that you can see, not more, by working in the pyramid. And that's why it's also important to know what this pyramid is about, right? And we have a big confusion what it is about when it comes to Sentinel-2 images. We don't know, right? But it's important to know because you're working in a pyramid most of the time. An interesting closing up an interesting activity that's currently going on is the ESA EOPF, the Earth Observation Processing Framework. The ESA has had, the lucid idea, the brilliant idea, whatever idea it is, to process Sentinel data as ZAR files. They say for the past decade, Copernicus Sentinel data processes have generated vast amounts of reliable, accurate Earth observation data that has facilitated groundbreaking scientific research and innovative commercial applications. But as technology evolves, so too must the data formats being used. Now we know that ESA created, the original form was these safe files, these sort of containers with lots of files, and then in them imagery as JPEG 2000. That was maybe, the biggest mistake of the previous century. And now they're essentially jumping over the cloud optimized GeoTIFF, this what kind of, large section of the Earth observation industry at least agreed upon as being a good idea. They're jumping over it and say, no, we're going to do ZAR. And we now wonder whether that will be, the next biggest mistake of this decade, or indeed a very good idea. And an interesting thing, ZAR is a cloud optimized format for imagery. It comes from the bioimaging. It's not developed in Earth observation. It has been adopted strongly by the climate and modeling communities. Well, here's a couple of things. We have cloud optimized GeoTIFF and ZAR as the two, I would say, the two contenders for cloud optimized data for imagery. A cloud optimized GeoTIFF is a file. A ZAR thing is a directory with files that are chunks. Here we have GeoTIFFs, we have bands, can have overviews. In ZARs, we have arrays. Arrays don't have overviews. You could create new arrays with the overviews, but then you don't have sort of easily the same tooling that you now have in Quantum GIS or something like that, right? The automatic reading. But of course, you could create it and you could sort of instruct and think of a convention for doing that. But I think they need to be, the overviews have different dimensions, right? So they need to be in different arrays, so in different ZAR stores. But let's see how they deal with that. Of course, GeoTIFF is focused on images, ZAR on arrays. So a lot of it comes from medical scannings, right? So 3D scans, that is from the CT scans and so on. So they are automatically 3D imagery where there is no, let's say, dominance of latitude and longitude as there is in the Earth observation. So we have Sentinel-2 is mostly latitude and longitude. It's mostly the pixel that is so small. Then we have the time every 5 days, but it's not like a video stream or so, right? Every 50 images per second. So it is sparse in time and dense in space. And ZAR comes from a different mindset where you have arbitrary dimension arrays, you just chunk them up. This has strong support in GeoNOS-Geo. For instance, coordinate reference system, the modeling communities like ERA5, CMIP6 that use ZAR, they're often worry much less about coordinate reference systems. They anyway work with geodetic coordinates, and quite often the world is round and not ellipsoidal, so on. And that's somebody else's problem. There is in that community strong support for X-ray, for Python. It uses the CDL, so this is what basically the successor of NetCDF, you could say, and uses CF conventions, which is good, right? Which is very clearly defined, but understood by the modeling communities and considered difficult often by the geospatial communities. This is high resolution spatial. ZAR is quite often high resolution temporal, right? If you think ERA 5 is, I think, 6 hourly data for 70 years or something like that, right? So there you have a real dense time axis. This has good conventions on where the colors go, where the category labels go. I don't think ZAR has that, but ZAR has units of measurements. So here we can do pixel order, interlacing, chunking is user defined, and in ZAR also chunking is user defined. So you can, as I said, you can do a good chunking for one and a bad chunking for another. So summing up, coming to the end, basically the cloud is just somebody else's computer, right? As we know, it's nothing more. It just has different sizes and somewhat different properties, and it costs money, but your computer costs also money, right? So if all is good, users can focus on problem instead of messing with files. That's the hope, it's the thing that Google Earth Engine brought to us, and what we try to also extend in openEO, where you work with image collections rather than with assets with individual files. Sort of this going through the files is something we should get rid of on the user level, right? Because it's uninteresting, it is just messy. Closed source code does not let it use scrutinize computational details and leads to a stronger cloud platform lock-in, right? If you invest all your time in Google Earth Engine, you cannot use that time or that work, you cannot use that for something else, right? If you, that is not, that is not the case if you use open source platform. Earth observation has long and particular history, as we saw, that sort of now, ended up in the climax of cloud optimized geotiffs. The modeling community has a different history that sort of led to NetCDF, and that is now sort of a data model that is being converted into ZARs because you can do it. The key behind fast access and processing is the chunking strategy, I think, which is not a fixed property of a file format. Like COGS and ZAR can both do that, but it's creator defined. The creator of the ZARs, of the COGS, chooses the chunk sizes, right? And they may work, and may network may work for application A. As I said, although ESA is currently allowed on the EOPF, ZAR for Sentinel, it remains to be seen if this is a better idea than storing them as COGS, which is what the sort of the US, the Earth and Amazon went with. They converted all the JPEG 2000s to COGS. The chunking further complicates this problem because you can create good COGS and bad ZARs and vice versa, and a chosen chunking strategy can be good for one problem and bad for another. So that complicates a fair comparison between one and the other considerably, I would say. This is what I wanted to say. Thank you.